Welcome to all of you. I am Dr. Parul Yadav, Assistant Professor at Department of Computer Science and Engineering in Institute of Engineering Technology, Lucknow. Today's lecture is on Syntax Directed Translation Scheme. In this lecture, topics that are covered are Syntax Directed Translation Scheme. Under Syntax Directed Translation Scheme, we will discuss synthesized and inherited translation, then translations on parse tree, then implementation of SDT. Under implementation of SDT, we will discuss SDT scheme for desk calculator, then implementation of desk calculator, then sequence of moves, and last topic is intermediate code, introduction to intermediate code. So, first is syntax directed translation scheme. Syntax directed translation scheme describes output to generate for each input construct. So, syntax directed translation scheme is a notational framework to generate intermediate code of the source program. It allows the compiler designer to generate intermediate code directly in terms of its syntactic structures of the source language. Syntax directed translation scheme is merely a context free grammar in which program fragment, that is also called as output action and sometimes called as semantic action or semantic rule, is associated with each production. So, here we will take one example. Suppose there is a grammar that is capital G, and in this grammar productions are like P1, P2 and Pn. So, in SDT we attach semantic action after every production like A1, here A2, here An. So, it is nothing but the productions associated with some action will be written, and now the output action, the actions that we are talking about, they can do the computation of values for variables belonging to the compiler. They can generate the intermediate code, this is most important objective here. Then the printing of an error diagnostic or the placement of some values in the table, that is table mean the symbol table. So, we will take one example. Suppose there is a production that is A2 XYZ and here output action is alpha. So, same it can be written as A2 X, Y and Z and action is alpha, plus here we have the substring that is W. So, we can obtain its derivation like A derives X, Y and Z. Now, this can derive W in 0 or more steps. So, we can easily obtain this derivation that shows that A can derive W in 1 or more steps. Now, just we will draw one parse tree for example. Suppose here start symbol of the grammar is capital S and that can be expanded to suppose A and B, and this A can be expanded using this production suppose X, Y, Z, and support has further alternates and they are marked suppose with some non-terminal with terminals like ABA. Just example we have, for an example we have drawn this parse tree. So, we know that the parsing, broadly parsing is of two types, top down parsing and in bottom up parsing. In top down parsing, we start to construct the parse tree from the root of the tree that is marked with the start symbol of the grammar, and we end at the leaf nodes of the tree that are marked with the terminals of the grammar. In bottom up parsing, we start from the leaves of the tree that are marked with the terminals of the grammar and we end at the start symbol of the grammar, mean we end at the root of the root of the tree that is marked with the start symbol of the grammar. So, in bottom up parsing, our objective is to know when to perform the action. So, in bottom up parsing, this action will be performed whenever there is reduction in the parse tree. For example, suppose at this level this X, Y, Z can be reduced to capital A. So, whenever we will do the reduction action corresponding to it will be performed. If we are doing the parsing using top down parsing, then the action is taken when x, y or z is expended. So, with respect to production, action will be performed. Now, we will see what is translation. A value associated with a grammar symbol is called as translation of a symbol. Suppose a grammar symbol is capital E, so its translation is suppose E dot val. Suppose we are talking about integer value to translation. So, one example is E dot val, it could be E dot val or E dot code, it depends. So, this is its translation, and every translation will have some value also. So, we will calculate this value also. Just take another example on production. Suppose this is the production E to E plus E. So, here in this production, actually on right hand side of production there are two non-terminals, and here we have same instance of same non-terminal. So, in that case, just to distinguish two non-terminals, they can be marked with superscript. So, this is like E1 and this is like E2, and translation for this non-terminal is E dot val, translation for E1 is E1 dot val, translation for E2 is E2 val, and we have written the rule combining all together. So, this is E dot val is equal to E1 dot val plus E2 dot val. Now, there are next is types of translation. So, there are two types of translations. First is synthesized translation, second is inherited translation. So, the same equation, same production and same action is written here over here. In synthesized translation, translation of non-terminal that is on left hand side of production is defined in terms of translation of non-terminals that are on right hand side of grammar. For example, E dot val is equal to E1 dot val plus E2 dot val. Now, in this next is inherited translation. Suppose production is A to X Y Z, and here semantic action is Y dot val is equal to 2 into A dot val. So, here translation of non-terminal that is on right hand side is defined in terms of translation of non-terminal that is on left hand side of production. This is Y and this is A. So, this is about synthesized translation and inherited translation. In today's class, we will discuss about the translations, and at all the places we will use synthesized translation. Next is translations on the parse tree. So, basically our objective is to get the intermediate code directly from the syntactic structure, but here we will design the SDT that is suitable for desk calculator. So, here the production is that is E to E plus C, then E to digit, and its semantic actions are E val is equal to E1 dot val plus E2 dot val, and this is E dot val is equal to digit. Here this E dot val is an integer valued translation. Now, we have the input string as 1 plus 2 plus 3. Next, we need to determine the values of translation by constructing the parse tree. So, here we will compute the values of translation that we have at each node. So, the parse tree, first is to construct the parse tree. For this input string, we can construct parse tree as we know E2, E plus E, then this E can be expanded to E plus E, then this E to 1, this E to 2, and then this E to 3. So, this is the parse tree. Now, we will compute the translation for each node. Now, here this is 1, this 1 can be reduced to capital E using production E to digit, and its translation is E dot val is equal to digit. So, this 1 can be associated with translation E dot val at this non-terminal. So, at this non-terminal we will obtain its translation as E dot val is equal to 1. Similarly, this 2 is reduced to capital E using this production. So, here we can write its translation as E dot val is equal to 2. Now, this is reduced to capital E using production E to E plus E. So, its semantic action is obtain value for translation of this non-terminal, then obtain value of translation for this non-terminal, and then do the computation using plus operator. So, here this is 1 and this is 2. So, 1 plus 2. So, here we will obtain value of translation at this non-terminal E dot val is equal to 3. Now, similarly, this 3 is reduced to capital E using production this. So, here we will obtain E dot val is equal to 3. And now, similarly, E plus E can be reduced to capital E. So, we will obtain value of translation as this non-terminal. This is E dot val. So, here we can write E dot val. Now, this is equal to translation for this non-terminal, value of translation for this non-terminal, this is 3 plus 3. So, here we will obtain 6. So, in that way we can do the translations on the parse tree. Now, next we will discuss the implementation of SDT. In practice, actually it is not always necessary to draw the parse tree. Without drawing the parse tree, we can implement the SDT using the stack based approach. So, suppose here this stack is actually pair of arrays and this pair has elements state and val. This state is entry to or index to LR1 parsing table, and this val is the value that we obtain for the translation. So, basically this is the stack, the pair of stack, this is for state and this is for val. Now, suppose production is A to X Y Z, output action is alpha and substring is W. Now, we can obtain the derivation like A derives X, Y and Z, and then this derives in 0 and 1 steps W. So, here first we will see the stack before the reduction. So, before the reduction here on a stack we have Z, this Z is there, then Y and then this Z, and in val portion we have associated translation value for respective non-terminal. So, this is top and this is suppose top minus 1 and this is top minus 2. Now, when this reduction will take place, mean this XYZ is reduced to capital A using this production, then we know that action will take place, and suppose action is related to that, here we are calculating value of A and for non-terminal. So, here we will obtain A dot val. So, actually whenever we perform the reduction, we will pop these non-terminals from the stack, we will reduce, we will update the value of top as top is equal to top minus 2, and here we will write the non-terminal A and its associated calculated translation. So, in that way we work on stack. Now, here we have possible set of productions along with its semantic actions. So, productions like S to E dollar, then E to E plus E, then E to E multiplication E to parenthesization of E, then E to I to I digit, I to digit. These are the productions and these are the semantic actions as we discussed in earlier case. Now, suppose this is the input string. Here we will try to see how the lexical analyzer, syntax analyzer and semantic analyzer are working together. So, just here lexical analyzer will scan this input string. Now, first symbol is 2. So, this 2 is actually a digit. Here the digit is ranging from 0 to 9. So, lexical analyzer will recognize that this is a digit. So, token corresponding to digit will be produced. So, this token will have two parameter. First is that this is digit and second its value, that is 2. That is 2. So, this pair will be created and that pair will be sent to syntax analyzer. Now, syntax analyzer will use this production, that is digit to I, and then this digit will be reduced to I, and then the semantic action will be performed. In this action, a value of its translation will be obtained, I dot val, this is equal to this digit, that is 2. Now, next is it will find 3. So, this is again token will be produced by the lexical analyzer, it will send to syntax analyzer, it will apply now this rule I digit. Now, here the semantic action is at this point, what semantic action will calculate I dot val. So, here we will calculate I dot val and this is equal to 10 into this value plus lex value. So, we will get 10 into 2 plus 3. So, here we will get 23. Now, next is multiplication. So, here we have multiplication, but no reduction will take place here. Now, next we have 5. So, this is the digit 5 here. Now, this 5 will be reduced using I. So, here I dot val is equal to lex val, that is 2. Now, this I will be reduced to capital E using this production. So, we will calculate E dot val. So, here E dot val is equal to I dot val, that is 2. Now, again similarly here E dot val is equal to I dot val. At this reduction we can calculate E dot val is equal to I dot val. So, this is equal to 23. Now, again there is one reduction, that is E multiplication E to capital E. So, for this we will apply this production and we will perform this action. So, in this action we will calculate value of translation at this non-terminal. So, this is E dot val. E dot val is equal to value of translation at this non-terminal and value of translation at this non-terminal. So, this is 23 multiplied by 2, not 2, this is 5 and this is 5, all right. So, 23 multiplied by 5, so we will get here 115, all right. Now, next is plus, so this is plus, but no reduction is possible here. Next is 4, so this is 4, again we will calculate I dot val using the same rule and semantic action, here we will get 4 and again here we will get E dot val is equal to I dot val. So, this is equal to 4. Now, next is this E plus E is reduced to capital E. So, here value of translation corresponding to this non-terminal and value of translation corresponding to this non-terminal. So, this is 115 here plus 4. So, 115 plus 4. So, E dot val now will be 119, sorry 119. Now, here we have E and then dollar. So, it is reduced to capital S using this production and semantic action is just to print the value of this E dot val. So, here we will print 119, E dot val is 119. So, in that way we can calculate the value of any equation. So, this is related to SDT of desk calculator. Now, we will discuss the implementation of desk calculator. So, here we have production and then we have its program fragment. Next is implementation of desk calculator. Here we will use the stack. So, again we have the possible set of productions S to E dollar, E to E plus, E to E multiplication E, E to parenthesized E, E to I to I digit and I to digit. Now, here we have the program fragment where we cause the compiler to execute the program fragment. So, here the program fragment is like E to E dollar. So, it will print the value that is at top minus 1 and then we are updating the top pointer. So, here suppose as dollar here the stack configuration will look like here like dollar at the top of the stack, then E, and answer is at here the value corresponding to this. So, this is top and this is top minus 1 index. So, we will print the value that is at top minus 1 index. Similarly, E to E plus E. So, here the stack values at particular stage will be like this. So, like suppose E1 then plus and then E2, and here this is top minus 1 and this is top minus 2. So, the value of this value corresponding to this non-terminal will be like value for translation for this non-terminal plus value of translation for this non-terminal. So, this is at top minus 1 index and this is at top index, and then after doing the computation they will be popped and top should be updated to top minus 2. So, in that way the program fragment will execute. So, here we will see the sequence of steps or sequence of moves related to the implementation. So, in this example input string has input string is 23 multiplication 5, and at last we have appended a dollar sign just to show the end of the string. So, here this is the production, some subset of productions has been written here, and this is the program fragment related to these productions. Now, here this is state and this is well, and on right hand side we have top of the stack. Now, first symbol is 2, this will be scanned 2. So, state is 2 and till now we do not have any value. Next is this 2 will be reduced to I, this digit will be reduced to I using production I2 digit, and here on the stack, on the top of the stack we will print the value, we will write the value 2. So, on value we have this 2. Next is 3. So, the state is 3 until now no value is onto the stack with respect to 3. Now, this 3 I3 using this production will be reduced to capital I. Now, here on a stack how computation will take place, actually on this stack this is at top and this is at top minus 1. So, 10 into top minus 1 plus this lax value 3, that will give us the answer, that is 23. And now we will update the top is equal to top minus 1. So, now this will be at top of the stack. Now, next is this I3 is reduced to I. Now, next is this I will be reduced to capital E. So, I using the production E to I and no semantic action is there. So, this I will be reduced to capital E and here there is no action to be done and production is E to I. Now, next is again we have written here some another set of required productions and their associated program fragment is written. Now, till now we are at step 6 where we have this configuration of input tape, state, value and the production. Now, next input symbol, scanned input symbol is multiplication. So, state will be this, and now at top with respect to multiplication we have nothing. So, this is the top and this is at top minus 1. Now, next is scanned symbol is 5. Again this will be at top and there is no value related to 5 till now. Now, this 5 will be reduced to I using production I2 digit, and in I2 digit at top of this value stack value part we will write this lax value. Now, and at the top we will have this the 5. So, this is now top and this is top minus 1 and this is top minus 2. Now, this I will be reduced to E using production E to I, and in E to I there is no semantic action. So, here there will be E to I. Now next is E multiplication E. This can be reduced to E using production, this one. Now here semantic action corresponding to this is that we know that this is at top and this is at top minus 2. So, we will take value that is on top minus 2, then value that is on top, and operation is multiplication. We will apply the multiplication on these values that will be stored at top minus 2 here. And now we will update our top pointer, that is top is equal to top minus 2. So, top index will be changed to top minus 2. So, this is at the top of the stack. Now, this E and next symbol is dollar. So, here we will write dollar and value corresponding to this is nothing. Now, next is that E dot dollar is reduced to S using production S to E dollar. So, S to E dollar. Now, this is action is semantic action is a program fragment is print value at top minus 1. So, this is top and this is top minus 1. So, value at top minus 1 is 115 and here top pointer is again updated, top is equal to top minus 1. So, in that way this example shows the sequence of moves that are required to implement. Next is intermediate code. This is also known as intermediate text. This text intermediate code is intermediate in terms of complexity between high level programming language code and machine code. It simplifies the tasks of generation of optimal target code. So, a compiler designer may directly generate the target code from the source code. But no doubt the target code directly obtained, the target code definitely will be efficient and optimal, but it will be very difficult for compiler designer to get the target code directly. Reason is that during the translation only designer will select the appropriate register and maintaining the efficient utilization of register also. So, task is very difficult. So, it simplifies the task of generation of optimal target code generation. It involves using at most one operation or one test in each step. It introduces symbols to stand for temporary quantities. There are 4 types of intermediate codes like postfix notation, syntax tree, quadruples or triples. So, this shows the 4 kinds of intermediate code and that will be discussed in next lecture, and in this lecture we have covered the SDTs. We talked about the translations, inherited translation and synthesized translation, then translations on parse tree, then we discussed the implementation for SDTs, where we design the SDTs that are suitable for disk calculator. We write the possible set of productions along with their semantic actions. We studied the stack based approach also, where the stack is a pair that has 2 pair of arrays, a stack and value, and we studied how to implement SDT using the stack based approach, and then we discuss the intermediate code. So, this is all about the SDT schemes. Thank you so much.